Attention, vous allez bientôt être en ligne.
Donc c'est quoi qu'en ligne, Julien? C'est la projection?
Voilà le lien, Laura.
Tu peux nous passer le lien super chat?
C'est effectivement le slideshow qui est en ligne. Il y a un décalage d'environ 30 secondes.
Tu me l'as envoyé par email, Julien?
Je te l'ai envoyé par Zoom et via Slack.
Okay.
Tu pourrais en envoyer par email, non?
Ouais. Ah oui, je peux me l'auto-envoyer.
Si tu envoies par email, est-ce que je peux envoyer aussi à Nicolas Papadakis? Tu as son adresse?
Oui, mais il faut que je sors alors de ça.
Ou sinon, tu m'envoies à moi.
Ouais. Attends, je me l'envoie.
Tu as prévu la liste ou pas?
Non, je l'avais renvoyé de là-bas avec moi-même. Non, je ne peux pas le faire moi-même. Voilà. Emmanuel. Je mets Nicolas
Ouais,
direction.
Nicolas, si tu
Tu l'avais pas
ouais,
maintenant?
parfait.
Bien.
Okay. Est-ce que tu veux que je l'envoie à des personnes en particulier ou...
Non, je vais le mettre par le chat là-bas et pour moi c'est bon.
D'accord.
Send it to me, I will send in the WhatsApp group.
On a perdu la présentation à l'écran.
Oui.
Et attention, Laura, il n'y a plus les slides pour l'instant.
Oui, c'est normal. Ok. Voilà. Là, il y a... Ça va venir.
Because I think nothing is connected. No one is connected. The only participant is you. I think the other, if you start doing the other one.
Can you send me the link on
you don't have to write just search YouTube.com. Try to open the
Okay. Share screen. Stop to share. Voilà. C'est bon?
le texte technique.
Ouais. Entkommt? Okay. Ok. C'est bon pour tout le monde?
Activer les caméras. Je vais vous
It's all right with me, Laura.
Vous m'entendez bien, c'est ça?
Oui.
Si.
Yes, we can hear you all.
Julien, tu réactives aussi les caméras. Ah ben voilà.
Ok. Tu peux me lever?
C'est bon pour toi, Laura? D'accord. Bon, on va commencer. Donc, toujours dans des conditions un peu particulières. Mais, voilà. Donc, on est ici pour écouter la soutenance de thèse de Laura. Alors, cette thèse, elle a été encadrée, elle a été réalisée ici à l'IGE à Grenoble. Elle a été encadrée par Emmanuel Thaume et Julien Le Sommer ici. Et c'était une thèse en co-tutelle avec l'Université des Baléares. Et on a Amanda Pasquale qui est en visioconférence, qui a aussi donc encadré cette thèse. Il y a deux rapporteurs pour cette thèse qui sont Kim Balabrera, qui est, je me rappelle plus le nom de ton institut, Kim, CSIC, voilà, à Barcelone, à Barcelone, et Rosemarie Moreau, qui est du Legos Toulouse. Et puis donc deux examinateurs, Francesco Doviglio, qui est chargé de recherche au CNRS et donc à Paris, et moi-même, Eric Guido, donc enseignant-chercheur ici à l'Université de Grenoble. Voilà. Donc écoute, on t'écoute pendant à peu près 50 minutes, et puis ensuite le jury te posera des questions.
Ok. Bon, merci pour la... Thank you for waiting with all the technical adaptations to this situation. So, well, as Eric Blay already introduced my supervisors and myself, there's only left to present the title of my defense, Image Denoising Techniques to Improve the Observability of Oceanic Fine-Scale Dynamics by the SWOT Mission, and also to thank the funding of my PhD to CNES and the European Commission. So, first an introduction. So, in the ocean we have a large range of scales and dynamics, and these have a wide range of spatial and temporal scales. And here we can class in these figures some processes in the y-axis in terms of the time scale and spatial scale. And for example, we can identify a process that everybody can see from the beach, surface gravity waves. And then for their study, we can divide these scales by a spatial scale of 100 kilometers. These scales actually, what it says is that above 100 kilometers, it's the larger scales, which we can nowadays synoptically reconstruct them at a global scale, but below this 100 kilometer scale, the phenomena are not as well reconstructed. And for example, at the large scale, we have climate change phenomena, like the warming of the oceans. And then at the fine scales, we also have processes like internal waves, which are similar to the surface waves we see at the ocean, but at the interface between layers. And we also have phenomena at the interface of these large and fine scales, which are, for example, these, which we can see here. Okay. So these fine scales, they vary in space and time. For example, if we look at this parameter, which defines the fundamental horizontal scale of mesoscale processes, we can see here the value of this radius in kilometers. And an important thing that it tells us is how, as we move away to the equator, the structures we find are smaller. But what does it also tell us? Above this scale, the Rossby radius of deformation, we are in geostrophic balance. And this means that we are in equilibrium between the Coriolis, rotation of the Earth, and the pressure gradient. And also, we can see in this equation that this horizontal pressure gradient, we can measure it by looking at the sea surface height of the ocean. Keep this in mind, we will look at it later. And also, these fine scales vary in time. For example, if we look at the seasonality of vorticity in the North Atlantic, here we can see an example of a small region in winter, and here in summer, and we can observe many more small-scale features in winter than in summer. But what is this vorticity value? Actually, vorticity is the gradient of the velocities, which we divide from our sea surface height, and give us information on the rotation of a fluid, and also information on the vertical velocities we can find in the ocean. So we have this view of the surface currents horizontally, and thanks to this parameter, also vertically. Okay, but why are these fine scales important? Why do we want to observe and reconstruct them globally? So here we can see the same figure of the eddies here, and between these two eddies we have a filament, and this filament, actually, what happens is that at this filament we have strong vertical velocities that have big impacts on biogeochemistry. As we can see here, you have a section, vertical section of chlorophyll, that is a parameter in the ocean that can tell us how much phytoplankton we have. And we can see that due to these vertical velocities, this chlorophyll maximum here is downwelled, and it has important impact for the marine ecosystems. Okay, so the fine scales have the importance in many aspects, but unfortunately, their study is limited due to observations. For example, here we can see all the observations we had in the European seas from January to March 2018, and although there are quite a lot, there's still not enough to synoptically reconstruct the fine scales. And then another important factor that limits the study of these fine scales is the complexity of the study due to the superposition of two types of motions, balanced and unbalanced. And okay, but what are these motions? So actually, a balanced motion is, for example, the mesoscale eddy we saw before, that we can find filaments between them. And an unbalanced motion example would be the internal gravity waves, the waves we saw that are found like in the interface of different layers in the ocean. And what happens actually is that, yes, there was an even smaller than eddies, we have the filaments, we have vertical velocities, and at an even smaller scale, we have these wave motions, and actually these different structures, they have a big impact on the ocean's energetic equilibrium and consequently in the climate, and consequently also in the climatic system. And this we can see it on this figure here, which the message to retain is that actually what happens is that the balanced motions inject energy towards bigger scale in the oceans, and these wave motions, the unbalanced motions, they inject energy towards smaller scale. So separating these two kinds of motions will be important to understand the energy transfers in the ocean. Okay, and a way to know about energy transfers in the ocean is SSH spatial spectra. Here we have an example of these variables from model outputs. You have here what would be the SSH power spectra, how much energy we have, and the wavelength is the scales. So what you can see here, we have more energy here than here. But first of all, what is sea surface height? As I told you before, we can derive this variable from pressure gradients in the ocean, and actually altimeters, satellites that we have nowadays, they can measure this variable by measuring this variable here, and from information we already know, like how high the satellite is, we can infer this variable here, which is the sea surface height. Okay, so okay, from this variable we can calculate its spectra that tell us its energy. So as I was saying, we know how much energy we have at the different spatial scales. And the important thing also to note is that as we move from bigger to smaller scales, our energy level decreases in general. Okay, and then also these SSA spatial spectra, they're useful because they can tell us information on this variable called the transition scale. What's the use of this? Actually, it let us know where we have balanced motions or unbalanced motions, the variables we were seeing before that are important for energy exchanges. So how do we use this spectra to know the transition scale? Actually, here we have this slope like this due to unbalanced motions at larger scales, and at a certain scale we have a change of slope which becomes flatter due to the presence of unbalanced motions. And this transition scale, we find it as this change of slope. So in this particular example, it would be around 80 kilometers. And that I was saying, this is important to know this parameter to better understand the energy exchanges, and also to know whether geostrophic theory breaks down. Okay, so we have seen different information about the fine scales, but how do we observe and simulate them? There has been a big improvement in recent years in situ and remote measurements, for example, but still we have a low spatial and temporal resolution to correctly manage to study the fine scale. And this is due to the coverage, for example, of our measurements. For example, here we can see an example of different satellite tracks of the satellite I was showing you before that measures SSH in the Mediterranean. And we can see that there are many tracks from 4 different satellites. But even so, there's still quite some big data gaps to study this phenomena. And also due to the resolution, for example, from all of this data we have, we derive certain products in 2D which are with a full coverage. But when we obtain these maps, the resolution is not also sometimes high enough to study the fine scale. For example, here in the Mediterranean, in one of the most recent products, we have resolution from 110 to 160 kilometers. So we cannot see a lot of the structures below this 100-kilometer scale we were seeing before. Okay, but we also have ocean models, and these ocean models, they solve an approximation of the Navier-Stokes equations to reproduce the ocean physical mechanisms. So we simulate, for example, the ocean currents, and they also have improved, and they reach now kilometric and hourly resolutions. For example, and starting to resolve the fine scale. And for example, if we look at the outputs of a particular simulation, the ENETL60, you can see here vorticity in the North Atlantic and Mediterranean. And if we zoom in to the Azores Islands, we can see all these very small features. So here we can see the fine scales, but what happens, there's different ocean models, and this one gives different results due to the way they're parameterized. And of course, as we were saying before, the validation with observations at these scales is difficult because we don't have a lot of data that actually observe these scales. But we hope that the future surface SWOT ocean topography mission will shed some light on this issue. It's a joint satellite mission between the NASA and NES with contributions of the Canadian and British spatial agencies. And what we can see is that this is like the tracks we were seeing before in the Mediterranean. And in addition to this track that we already have data from today, it will have these 2 SWOTs here, which will give us a 2D vision for the first time of the ocean from SSH data. But it will not be launched until 2022. So we can also observe that we have these 2 gaps, these 2 SWOTs, which are 50 kilometers. And we have a gap at the center where there's this nadir data, which is 20 kilometers wide. Okay, other characteristics of the satellite mission is that it will have 2 orbits. So firstly, after the engineering checks, it will have a phase called the fast sampling phase, which you will have a 1-day repeat cycle for the first 90 days. And this fast sampling phase will be used for calibration and validation of the data. So actually, this 1-day repeat cycle, what it means that here we can see the satellite tracks over the globe. And so every day we will have all of this data. And then there will be this, for example, in the Mediterranean, we'll have this crossover of these 2 passes where even more calibration and validation experiments will be possible. Okay, so after this phase, we will have the nominal or science phase, so it will be 20-day repeat cycle. So it will take more days to have all the different passes, but as you can see in this example here, the coverage we will have, for example, in the Mediterranean will be much higher. But for us, in what follows, we will focus mainly on the fast sampling phase, and now I will show you some sections of this SWOT here. Okay, so with the satellite, there will be also spatial noise and errors associated, and they have different sources. Here we can see some examples from the a priori noise and errors. And we have different types of noise, ones which are instrumental. For example, this roll error will be due to the satellite's rolling. And then other ones, like the 2 beam path delay, due to geophysical phenomena like the wet troposphere. And also we can class them by the type of spatial error correlation, and we can see that only this carrying error is uncorrelated in space, and these ones are spatially correlated. You can also note that the color bars here are different, and actually the 2 errors which will be stronger will be the roll and the phase error. Okay, if we focus on these spatially correlated errors, they are actually strongly correlated across track, known locally or locally, but they also have these non-local correlated errors have an uncorrelated error component along track at the small scales. Okay, and then if we look at this uncorrelated error, the cap and radar interferometric error, it's spatially uncorrelated across and along track. And also its noise level will depend on the surface wave thickness. So here what you see is that as we go from the center of the SWOT to this outer border, firstly you can see that for a particular sea wave height, the noise level varies and it's higher at the borders, and then we can see that as the sea wave height increases and consequently the wave thickness, so does the noise level. For what follows, actually we will keep this in mind, but we look at a constant carrying noise level for a sea wave height of 2 meters. Okay, so this uncorrelated error will a priori dominate scales from what the estimates we have of less than 50 kilometers. So we won't know if we will observe the unbalanced motions I was mentioning before. And also it will affect our ability to compute derivatives. Meaning, for example, will we see the surface currents and vorticity variables we were seeing before. So here you have the noise-free images. So here is SSH without any noise. And this would be the first derivative and second derivative, we would correspond to the surface currents and vorticity. But what happens when we add noise? Here we can see that SSH is a bit noisy, but we don't see anything in our derivatives. The noise completely masks the first and second order derivatives. So we need to find some specific processing algorithms to maximize the benefit of this data. Okay, so by why do we need to reconstruct these SSH derivatives? So as I was saying, we need to obtain physical variables like geostrophic velocity and vorticity, and more, of course. But also, there are data simulation methods like Ruggiero et al. 2016 that use the information on the derivatives to remove these correlated errors that we saw before. Okay, so what were the questions I asked myself at the beginning of this PhD study? Firstly, what would be the best method to remove the small scale and correlated noise while conserving the SSH signal and the structures? And secondly, what will be the effective spatial resolution of the denoised SWOT data on the swath in different regimes? So in other words, will I be able to see the fine scales from the SWOT data? And to do this, we use observing system simulation experiments and filtering with different image denoising methods. So here's the outline. I did an introduction that hopefully will help you follow on what follows. And now I will present you some results on the SWOT scales from simulation, of course, always, the different filtering methods I used. Then we will revisit the SWOT scale once we apply the filtering. And finally, some results on calibration of the filtering method and the usual conclusions and perspectives. So just for the SWOT scale, as I said before, the satellite will not be launched until 2022, so we need to simulate the data. For this, we will use the ocean models, and as I was saying before, there's no perfect model at these fine scales, so we use a range of different models to account for all the different plausible scenarios we could have. Here are the 5 different models we used. What is important to retain from here is that they all have small horizontal resolution from 1 to 4 kilometers, permitting the existence of the fine scales. And also that these 3 models have tidal forcing. And why is this important? Is because when we have tidal forcing, there will be higher presence of internal waves in our model, which will have an impact on the SSH spectra at the fine scales. So, okay, we have our input data, and the last thing we need to generate the SWOT data is the SWOT simulator, developed by Gaultier Nubelman 2015, but kept up to date all these years. And firstly, what the simulator does is generate the grid files of the satellite. So we say which area we want to look, for example, the Mediterranean, and it gives us all the different satellite passes. Then it interpolates the model input, in this case the WMOP, linearly in space into these different grid files we have. Then we obtain, consequently, after interpolation, these passes. Here we see an example, and we obtain a first variable called SSH model, which is the simulated SWOT data, but without noise. And lastly, the simulator adds noise, which is added to this variable here, and we obtain this last variable, SSH ops, which is the noisy SWOT data. Okay, but how is this noise generated by the simulator? Actually, these SWOT errors are generated randomly from a spectral error model, which is shown here. But what is important to retain from this figure is that, firstly, these errors, they are a priori errors, that like the examples we saw before, and they don't vary realistically in space and time. So it gives us an approximation, but for example, the error level we get for example, the 1st of February will not be realistic to the data on that specific date. And also that the spectra that has the highest value, so the more noise at these fine scales which are found here, is the carrying noise, the uncorrelated error that we were seeing before. Okay, so we have our input data and the simulator. So we focus on the fast sampling phase, which I show you here the tracks again. And why do we focus on the fast sampling phase? Firstly, because thanks to its one-day repeat cycle, having all of these tracks every day, we have a high number of passes, so a lot of data to test, and also because it will help prepare for the calibration and validation experiments before and after the launch of the satellite. But we specifically focus on 4 regions here in the Pacific, the Gulf Stream, the Azores Islands, and the Western Mediterranean, in different crossover regions where 2 tracks cross. And we focus on these 4 regions because they have contrasting dynamical regimes. For example, high-low mesoscale eddy kinetic energy, for example, high in the Gulf Stream but low in the Mediterranean, and high-low internal tide signals. For example, we have these higher signals here in the Pacific and then the Azores. Also, these areas are well documented in several papers. And lastly, what we do is also simulate this data for winter and summer. So we can compare the outputs. For example, if you remember at the beginning that we saw how in winter and summer we had different size of the structures. Okay, so we have our data and our simulations, but how can we know which is the smallest result scale by SWOT? So, okay, we draw different data for winter and summer from the simulator, and we include the SWOT errors thanks to the SWOT simulator, and we use the power spectra. As I recall, here is the SSH spectra, the energy, how much energy we have, here the wavelength, so big scale here, small scales here, and we calculate the 1D power spectra in the long trunk direction, and then average across track for all the passes we have, for example, during winter, and in this example will be for MIT GCM outputs in the Azores region. And we calculate this for our noise-free data, SSH model, and also we calculate the residual noise. How do we do this? We look at the difference between our noisy data and our noise-free data, so we obtain the residual noise, and calculate, like before, with this same methodology here, the spectra of the residual noise, which you can observe here. And then what we do, we find the smallest scale by looking at where these two curves intersect. And in this case, it would be here. Why this intersection? This intersection actually gives us an approximation of where the signal and noise are of the same order of magnitude. Okay, so we do this for all of our scenarios, and we obtain this data. On the left, you have the winter data, on the right, the summer data, and then for the three models we use with tidal forcing, NEMO, HICOM, and MIT GCM, and for our four regions, Azores, Gulf Stream, Pacific, and Mediterranean. And what is the first thing we can see? Our SWOT scale, LS, has a big range from 27 to 66 kilometers. Then we can also see that MIT GCM has systematically a smaller value than the other models due to its different configuration. And then comparing the regions, in the Mediterranean, the values are closer, but then in regions like the Azores or the Gulf Stream, the variability is higher. And all of these differences occur because of the different dynamical regimes that I was mentioning before. Okay, and if we compare these scales with a transition scale, which I recall is where we go from balanced to unbalanced motions, what we can see is that in some cases, our SWOT scale is below the transition scale, and in other cases, it's above. What does it mean? When the SWOT scale is above the transition scale, it means that we will not be able to observe unbalanced motions like internal waves from the SWOT data. So we can see that depending on our scenario, we observe or not these motions. But we actually think that this noise level we have here can be reduced by removing some of the SWOT noise which dominates at the small scales, the carrying error. And there are different filtering techniques that exist to do so, but we need to know which one is the most efficient for our objective here. So, okay, moving on to the filtering. First of all, what is a filter in an image denoising context? We can define it as if we have an image, it's a recalculation of this image by using the information on the surrounding points. And if we look at an example, here in black you have a noisy curve, and once we apply a filter to smooth this, the curve becomes much smoother and we reduce some of the variability of this curve. Or maybe an example that we all use more daily, for example, when we blur our background when we are talking in Skype and we don't know, and we don't want somebody to see what is behind us. But for us, actually, what is a good filter? Us, we need a filter that manages to preserve the different oceanic structures we have present or in other words, the phase of the SSH signal, and also that it manages to preserve the intensity of the SSH signal. So actually, in the context of the SWOT mission, there has been previous studies that have tried to do this, like Shelton et al. 2019 or Gautier et al. 2016, and they've shown that different smoothing methods manage to remove the uncorrelated noise and errors. For example, here we can see the absolute just traffic velocity in the Gaussian region, and here is the noise-free data, the SWOT data with the noise. And you can see we don't observe anything anymore. And here what they obtain with the method. So they recover the structures, but it's still a bit noisy. So as we explore these smoothing methods, and we focus on the Gaussian method, which is a classical method where we can smooth a signal at different scales in space. And we test this method in 2 OSSEs in the Western Mediterranean. And in both scenarios, we observe a reduction of the noise level, but we see that in removing the small scale noise, we remove part of our signal too. Okay, so here we see again the SSH spectra and the wavelength, big scale, small scales. And in red, you have the SSH spectra of our noisy data. So you can see this level, the noise level here at the small scales. And in blue, you have the SSH spectra noise-free, so that what we want to obtain. And in green, you see what we obtain after applying this filter. So what we see that in removing the noise, we also remove part of the signal. And this happens, for example, when we want a noise-free vorticity, so the second derivative of SSH. And then if we look, for example, at the best configuration, the Gaussian filter configuration that would give us the best SSH spectra, we see that even in this scenario, again in red you have the noisy spectra, in blue the spectra we want, and here it's in black the filtered spectra. We see that although it is much better, the filter doesn't manage to act adequately at all scales. But the main limitation of this method is that in removing the small scale noise, we remove part of the Oceanic signal. So we need to investigate further and find a method that better preserves the gradients and their intensities. So we explore the derivatives penalization method. This method is an image denoising method based on penalizing the derivatives of first, second, or third order of an image, or a combination of them. And how do we do this? We have this cost function, g of h, that we want to minimize. And actually this function, what it does, it has two types of terms. First, this term here, that is the distance to our image, what we want to recover, our observation. And then we have these three terms here, which penalizes the image of the first, second, and third order derivatives. Why is this interesting for our case? Is that here, with this first term, we are penalizing the SSH, here the first derivative, the velocities, and here the vorticity. So we manage to adapt this method to our particular case in a physical sense to recover down to the derivative that we want to recover, the vorticity. And the minimization of this cost function is implemented iteratively with this algorithm function here. And a big part of my work was to see how we implemented this function. And one of the first things, of course, as it's an iterative method, was to set like the maximum value or convergence criteria. But also, there was two things we had to do. One was the preconditioning. It's an iterative method, so it can take a lot of time until we find some convergence. So one of the things we did was use a preconditioning that what it does is that accelerates the iterations, and if the preconditioning is well posed, it will not change our final image. And what the preconditioning is that at iteration 1, instead of using our noisy image, we can use a smooth image, in this case a Gaussian filtered image, so that it goes faster. And then, if you remember, I told you that there was a gap between the two SWOTs, and to decrease the inner border errors, so the error at the borders between the gap, we used a gap filling methodology. So we put some data in the gap, which also is called inpainting. So this way we could more easily calculate our derivatives to implement this method. Okay, and also to see what were the different stages of this method. So we start HOBS in this equation will be our noisy image, our observation. Then, as I was saying, at iteration 1, we have our preconditioned image, so this image with the Gaussian filter and with the inpainting, so with the gap field. And then after several iterations, at the end, when we have some convergence, we find this image here. And as our motivation was not to provide a gap field image and to better compare it with our initial observation that had a gap present, the last step is to mask this gap to obtain this image. Okay, so with all of this setup in place, the only thing we have left to parameterize is these different lambdas here. That these lambdas will tell us how much we need to penalize our different variables. SSH, the gradient of SSH, and the Laplacian of SSH. So we can make a choice of to penalize only this, or combine all these parameters. Okay, but how do we know which combination we choose? So we base our diagnostic on root mean square errors, and we don't only do them on the SSH, but also the gradient and the Laplacian, so we can make sure that the phase of our SSH signal is correct, or in other words, to know that we recover correctly our structures. And we also use spatial power spectral densities, so the spectra we have been seeing all the time, and we compare our filtered spectra to the noise-free spectra we want to obtain, and this will tell us information on the intensity of the SSH signal. These calculations on the RMSE were done, but in what follows, I will focus on the SSH spectra. And actually, for the SSH spectra, we developed a special score called the mean spectral ratio that actually, we see this here, but it's like a normalized difference between our true spectra and our filtered spectra. Okay, so we normalize it by the wavelength, and so we calculate this score for every lambda we test. For example, here we see an example of different lambda 2s we've tested, and here is the value of the mean spectral score. And here we can see an example for the Western Mediterranean, for winter and summer, for the MIT GCM outputs. And what is important to note is that this score here, the MSR score, the lower it is, it means that the closer our filtered spectra is to our true spectra, what we want to obtain. So we can see these curves here, find the minimum point, and when we have this minimum point, we go find our optimal lambda 2. And for example, in this case, for winter, in the Mediterranean, it's about 5, and in summer, it's a bit higher, about 20, which also makes sense to what we had seen before, that actually in winter, we have smaller structures, so more energy, so we need to penalize less our image. Okay, so we look at these scores for all the different combinations, only lambda 2, and lambda 3, and we apply these scores, and we look at which combination gives the best scores, and we actually find something good with this, that we only need one parameter, which will make it easy to tune. And this parameter is lambda 2. So this is the cost function that we have at the end to minimize. So the only thing we are left to penalize is the gradient of the SSH. Okay, so what does the data look like after using this parameter? Actually, as I was saying, this filtering method was intended to focus for the carrying error. So as a control experiment, we also simulated data, SSH OBS K, with only the carrying error to see if, without the correlated errors in an ideal scenario, our method worked correctly. And then we also simulated SSH ops with all the other errors to see how it would turn out in a more realistic case. So let's see, here we have the SSH, the gradient of SSH or the velocity, and the Laplacian of SSH corresponds to the vorticity. And here is the images we want to recover, which are noise-free. This with only the carrying error added, which again, we can see how the derivatives are completely masked by this error. Here, when we have all the errors, here I put you an example where you can see that actually there's how values here at the sides due to the high presence of correlated errors. And this is the images we obtain after filtering. And you can see that we manage to remove the noise and to recover the main structures present, as well as the intensity. So the order of magnitudes of the variable correspond to the image we want to recover. And we can see that even in a high presence of correlated errors, our images are recovered. Okay, so this we could say corresponds, give us some information on the phase of the signal. What about its intensity? If we look at the spectra of 3 scenarios for summer, winter, and summer, again of another simulation year, in black you have the noisy spectra, in red the spectra we want to recover, and in blue the spectra we obtain with each of the scenarios optimal lambda 2, and we can see that for all scenarios we managed to reduce the noise and come very close to the spectra we want to recover. And okay, if we compare this to I showed you before some spectra on the Gaussian, and now some spectra of our derivatives penalization method. Here we see again the 3 season scenarios, and in green you see the mean spectral score for the Gaussian, in blue for the derivatives penalization, and you can see how for all 3 scenarios the score for the Gaussian is much higher, and consequently it's further away from our true spectra. So okay, we found the best parameterization, the best method, its best parameterization. Now we can revisit our SWOT scales after applying the filtering. So the first thing we have to do is find the optimal lambda 2 for each scenario. So for each region, model and winter, northern hemisphere winter in blue, and northern hemisphere summer in red, we find its optimal lambda 2 value using the mean spectral score, and we filter the data, and we obtain again with the same method the SWOT scales. So here we see the tables like before, winter and summer, and in the left you have the initial SWOT scale we had seen without filtering, and on the right in bold you have the SWOT scale we recover after filtering. And what we can observe is that there's a systematic reduction of the smallest observable scale, so we managed to reduce the SWOT scale in all scenarios, and in some cases, for example here summer MIT GCM Azores, the SWOT scale is reduced by more than 50%. So another way to evaluate the benefits of this filtering is, in addition to the reduction of the SWOT scale, is how much noise we've reduced, the percentage of noise we've reduced. So what we do, here you have the different percentages, and what they show, here we see again the spectra of this is the SSH model spectra, and these are the residual noise spectra, here without denoising, so our initial noise, and this is the residual noise after denoising, and we can see that at the beginning we had this SWOT scale here, we moved and managed to reduce the SWOT scale to this value, but in addition we see that at this scale here in particular, we've managed to reduce our noise by 82%. What does this mean? That even below this scale, we've managed to reduce our noise by a lot. Okay, and then if we now compare again our SWOT scale to the transition scale, so will we observe the unbalanced motion and thus internal waves? This is the information we had before. What did we know? That in some cases, yes, just a little bit, in some cases no, it wasn't very sure, but here we have the comparison of the transition scale with the different SWOT scales, and we can see that once we apply this filtering, in all scenarios, we can manage to observe these unbalanced motion signals, so to better study the energy exchanges in the ocean. Okay, so moving to the calibration of the filtering, this is the last part of the results, and it's important because all the denoise data is found in an ideal context of OSSE experiments, but of course how we will be able to tune our filtering, our lambda2, with the real data. What I did a sensitivity experiment of the optimal lambda2 values in relation to the SSH spectra at different wavelengths. So okay, here what I show you is in blue is the values of the different mean spectra. So for example, in summer for the MIT GCM in the Azores region, we have one blue dot. Then all the cloud of dots you have here, with here the density of points, is, for example, cycle 1, pass 1 of the summer of MIT GCM in the Azores region. So what we find, I did different tests, so what is the relations of optimal lambda2 and SSH spectra at different wavelengths, and I found that if we were at a 30-kilometer wavelength, there was this log-log linear relationship between the optimal lambda2 and the 30 kilometers. So we could find that as the SSH spectra value at 30 kilometers increases, the optimal lambda2 we have decreases. And this linear relationship was found both for the mean points as well as for the cloud of points. So with this log-log linear relationship, actually we can infer the optimal lambda2 values from, for example, spatial spectra of the SSH data we have from the today's altimeters. And here we have, for example, the value, the SSH spectra value at 30 kilometers from a particular altimeter, Saral Altica. And so we have the values all over the globe for the winter, summer, and average all over the year. So for each of these data points, we can use our log-log linear relationship and obtain global maps of lambda2. So we have a possible method to tune our filtering once the satellite is launched. Okay, so finally moving to the conclusions. To give you a bit of context again about this work, we have the SWOT science team that has different objectives, like better measuring vertical exchanges, energy exchanges, and observing internal waves and balance motions. But in order to reach these objectives, we need horizontal velocity maps. And to get to these maps from the SWOT data, we need to denoise the SWOT and to use data inversion methods. And thus, we managed to solve this first processing step, opening the door to other processing steps in order to exploit the SSH data and its derivatives on the SWOT, finally reaching these objectives. So, coming back to the questions I asked myself, what is the best method to remove the small-scale noise while conserving the SSH signal and structures? And the second question was, what is the effective spatial resolution of the denoised SWOT data? So for the first question, we found that the derivatives penalization method fulfilled our objectives, and we managed to remove the correlated noise whilst allowing the observation of not only SSH, but also its gradients. And we developed a code that is now freely available on GitHub. Then for the second question, we found the finest SWOT spatial scale pre and post filtering for different regions and seasons. And we found this range of scales, of filter scales using the different range of models we had. And we found that even in all the different possible scenarios from different models, in all cases, by using the filtering, we managed to go below the transition scale and consequently observe the internal waves that the SWOT science team is interested in seeing. And also, we can see that these results contribute to the observation of the fine scales in the future SWOT data, as we managed to obtain the first and second derivatives, and so the velocity and vorticity. And what would be the perspectives? We could say that pre-launch or in a short-term scenario, we could expand our OSSEs to different crossover regions, and also to apply this method to the science phase, as not only we developed a denoising method, but also a methodology to evaluate it. Then we could improve our denoising by looking further into the impacting, as we only used it as a technique to reduce our derivative errors, but it could be interesting to have a complete 120 kilometer swath, and also to exploit the nadir data that is found in this gap, for example, cross-calibration. Then we could make the method more operational by studying further our filtering calibration, and also, as I said before, we only used a carrying noise level for a sea wave height of 2 meters, but we could explore what would happen with different carrying noise levels. And then combine our method with other SWOT-specific processing algorithms to remove, for example, the correlated errors, like, for example, the studies done by Metrez et al. And in the more long-term or post-launch scenario, as we managed to retrieve these variables here, the velocity and vorticity, we can exploit the benefits of using SWOT data to capture geostrophic currents, but also, as we go below the transition scale, what are the limits of the geostrophic theory in deriving velocities. Then we can exploit the knowledge that SWOT can render on the surface currents for new satellite missions that use Doppler radar measurements. Also, to, for example, study the kinetic energy fluxes, again, because we managed to retrieve the unbalanced motions. And also, we can, as we have this noise-free vorticity, we can explore the derivation of vertical velocities to better understand the ocean in 3D. Okay, so thank you very much to everybody. I'm sure I forget somebody, hopefully not. And thank you again.
Merci beaucoup. Bon, merci pour cette excellente présentation. On va pouvoir passer aux questions, en commençant par les rapporteurs.
Okay.
Ouais. On va laisser Laura voir un tableau.
So I can just...
Et puis, du coup, Kim, si tu veux commencer.
Okay. Okay, I'm going to make my questions in English. First of all, Laura, congratulations for this work, for the presentation that has been extremely clear. I extend these congratulations to your directors, because this is a work with really good quality. I'm a specialist in another satellite mission, so I'm not specialized in sea level. I've worked more recently on a small satellite, and while reading your report, I couldn't find plenty of useful information. And comparing missions with missions, when I see your choice of methodologies, the questions, the metrics that you're using, I can say that I have all the choices looked robust to me. They were looking the correct ones to be taken. So from the technical point of view, I have no practical questions for you. About the quality of the report, I have to say that I found, as I said in my report, a difference between what are the chapters already published or ready to be submitted as a very well written, but I found that the introduction of your report was the weakest part of all this work. I'm not going to go over the details, because there are plenty of things about language. There were things about information that for me was not that useful. I'm not going to give over that, because I think that by you revisiting this with your supervisors, you're going to be able to make it a more focused on the topic. So the questions that I have, it's more on the fly questions that appeared when I was reading the report. So in the introduction, for example, when you list advantages of combining models and observations, you say two. There are two advantages. One is for model validation and for data, or using the model to interpolate the data. Can you think about other ways to combine data model other than model validation and data interpolation?
I think, like, for example, yeah, again, like in a multi-platform approach, also when we have like without interpolation already, if the model includes, for example, data simulation, if, for example, it coincides that we don't have a, I don't know, a satellite pass, we can use, for example, the model outputs to have an estimation of what data to observe, for example, when we are at sea.
All right, but do you think that models, it's a question, do you think that models are good enough at this moment to be used to check or to validate observations?
I think it depends on what we want to validate exactly, because it's a bit, how do you say, like you don't know what is best, because, for example, as I was saying, the fine scales, there's not a lot of data to validate the models at these scales, so then we don't know if we can use it back to validate the models to the data. But, for example, I can think that also a bit more, how do you say, more theoretical models or simulations can be used to better understand the processes, to then know which is more realistic according to the theory we have, for example, the observation or the model.
Okay, fair enough. Thank you, Laura. Again, in the introduction, when you were reviewing the different satellite images in the report, you were talking about SST, SSS, and ocean color, and there was something that surprised me, because you said that ocean color is not directly observed but estimated. You said it's for ocean color. It's not the same for everyone?
Yeah, it's true that we could say that it's not, we don't measure exactly SST or SSS, we measure other variables from which we infer, that the raw data, in a sense, is not those variables, I agree.
Okay. In the figure 2.7, in your
okay,
2.7 top Atlantic January.
Nearly. Okay, yes.
Yeah, you have it. The question I'm going to ask does not change at all the conclusions drawn from that plot, but have anyone looked at the impact that outliers might have when making the empirical regression? Because when you go at high significant wave height, those are outliers, and those outliers are giving you the shape of the regression is given by these points. Have anyone looked at what happens when you remove those points in the regression?
Actually, I don't have that information, because it was given by some colleagues. We obtained this figure just to, for example, I showed here that we have information about the careen noise level with the sea wave height, with the variation of the sea wave height, but the wave stiffness might also vary with the wave period. And these plots would also just to prove that in some regions like the Mediterranean, it was important maybe to have this information of the noise level with the wave period, but I don't have the exact details about this wave value regressions.
No, and
But yeah, it would
as I
be
say,
interesting to know, but yeah, that I don't.
More than
I don't
interesting
really.
to know in this case, because as I repeat, I don't think that if you remove these outliers, your conclusions or the information that you retrieve changes much. But for example, when you do the calibration, always be aware that outliers, especially there are some outliers that if they appear or not, they're not appear, the shape of the regression of the curves change completely. So something to be aware of. In section 5, when you're saying, okay, let's see what we can see, from SWOT data, scale results. You put yourselves into the first part of the SWOT mission, no? That it's 3 months with 1 day sampling. I understand going for the 1 day sampling. Did you keep it at 3 months? Because most of the things that you are evaluating come from averaging, lots of averaging. You're averaging over the whole period. How your conclusions, your results are good. It's not that you need to change something to get good results. The results are good, but how these results will change if you change the period of the study? So rather than 3, going to 6, going to 4, going to 2, going to 1. How do you think it will change?
I mean, I think there's, well, at least in this scenario, what will change, of course, if we move away, for example, from winter in the northern hemisphere, the energy spectra we will have will become lower. So the first thing that will change, like the SWOT skills, of course, will vary with the time period we choose. And also, of course, then our filtering parameters need to be adapted. So there's this both like in a physical and more technical sense for us. And yeah, I mean, like, yeah, of course, everything will change and have to be adapted because, yeah, we have these dynamical variations in time as we saw, and also the parameterization that is based on that. And of course, yeah, it might change also if not only we shift these 3 months, but also change the duration 1 month to 3 months. But I think, yeah, that the main conclusions would still hold.
Okay. Now there are more and more coastal simulations with resolutions going to as fine as 200 meters. Do you think that these simulations can be used to study SWOT reveals near coastlines, or the nature of the being so local will prevent any use of these local simulations?
I mean, also, like, I think a big benefit that the altimeter community will have from SWOT is that we will manage to have data closer to the coast, because if I remember correctly, we will not have so much noise due to the transition from ocean to land. But of course, yeah, there's always a limit, and I don't know. Yeah, I think maybe that the resolution of the data of SWOT, even if we manage to go to really small wavelengths, will not be able to reach 200 meters, because I think that at those resolutions, the noise level will be so much higher than our signal that there's not much that we could do.
So it's more important the extent of the model in that cases than not the resolution of the model.
I think that of course, I think it would be beneficial that, of course, the finer resolution we have, the better we will resolve the fine skills, like above these 200 meters. But like, it's like, of course, the data we will have of the oceans will be better, but I think that the SWOT mission might not need as such fine resolutions, given that its a priori objective is to resolve wavelengths of 15 kilometers, so structures of 7.5 kilometers.
Thank you. Perfect. Last question. In the introduction, you gave a brief description of the classical processing structure used in altimetry of level 0, level 1. Your work is on level 4 products. Do you think that your work could help improve lower level products and how this could be done? So can you provide any information that people working at level 3 could use to check that their level 3 is as good as it can be?
Sorry.
Yeah,
of course. Last question. I think maybe there's some. I mean, this method, as it was very focused on the derivatives, but I think that at other levels of the processing, it could be interesting. For example, for the, if I may say it correctly, to derive, for example, also SWOT intends to better improve the geoid measurements we have. So I think maybe this method could be adapted to this kind of measurements, which would affect also our final product. But I mean, I think like the concept that we introduced here, yes, that it could be implemented not only at other levels of the processing, but of course to other kind of data where the derivatives of the image are important.
Okay, that's all from me. Again, thank you very much. Congratulations for this work. Congratulations for your presentation and congratulations for your answers.
Yes, yes.
Thank you, Kim. Okay, the second rapporteur is Rosemary. Rosemary, it's up to you.
Okay, can you hear me, Laura?
Yeah, it's okay.
Yeah, well, I'd also like to add my congratulations to you because I very much enjoyed reading your thesis, and your presentation was a very clear presentation, and I also appreciated in your presentation the effort you had made in the introduction to be concise and logical in the presentation of the background material, so that was very good. And also you have extra work that you had done since the end of the thesis that's included in the oral presentation, and so I really appreciated that too. I guess from the SWOT community perspective, one of the key aspects of this work is that there are a lot of the SWOT community who are looking at downstream applications of the SWOT data, and you have made one of the rare PhD theses that's really dedicated to trying to understand how we're going to get the best basic data that we can use and to reduce the noise. Can you hear me still?
Yes, me I can. Wait, I'll try to at least mute this.
Okay, because
okay, I can't.
you need to apply your noise reduction to the guys working out the back. Okay.
Yeah.
Yes.
At least it's in the theme of your PhD thesis.
Yes, yes.
So I think the steps that you have done in terms of filling the gaps and exploring more intelligent ways of doing the spatial filtering, it's very, it's really key results for everybody who will then be using SWOT data. So I think with the help of your thesis supervisors, you've really made a huge step forward in our understanding of how we're going to use SWOT data for the downstream applications. I gave you a whole lot of comments in the written report, which I won't go back through, which is also because there was a lot of interesting work, and so I had a lot of interest and a lot of questions and comments. I guess because you have this slide up with the position of the swaths, and there's a couple of questions I'd just like to ask you. When you're doing the in-painting, could you explain exactly what sort of interpolation you do to fill the gaps?
Actually, it's not an interpolation. What we do is that we use again like this Gaussian image filter, and actually like I use like another like technique that is used in other scenarios, like for example to deal only with the presence of nonce when we filter, and is that let's see if I can explain it without the additional slide. But yeah, I apply the Gaussian filter and then I apply also the Gaussian filter to the mask and then combine these two images. So at the end, I fill in the gap by weighting the gap also with this Gaussian image. I don't know if it's very clear, but so yeah. So
and
actually,
the scales,
yeah.
Sorry, the scales of the Gaussian image, are they close to what we resolve with DUAX now or not? With standard altimetry maps now?
I think,
Or is
I
it
don't know,
smaller?
like I remember the sigma is of 10, but yeah, I don't remember exactly what is the parameter you use for DUAX. But first, yeah, I did some tests to see that it wasn't something that we looked into a lot, because first it was just to reduce the inner border derivative error. So until when we had something acceptable, we're like, okay. And then yeah, we saw that this could be further improved, as it's an interesting part of the processing. But yeah, I didn't look at it in much more detail.
Yes, because as you mentioned in your perspectives, there are a lot of applications of using the SWOT data, but if we're limited to 50-kilometer grids, it is slightly less interesting than if we have 120-kilometer grid. And so having good gap filling is also very good for calculating 2D energy fluxes or different things from the final products. And you mentioned in the perspectives that you haven't used the error structure across the SWOTs, that sort of smile error structure.
Yeah.
And have you thought about using the NADAR data that will be available in the gap with a higher error level and trying to fill the gaps using also the information on the errors in the SWOT, but also the error at NADAR?
Yeah, I thought that it would be interesting, well, to do like a small test, if it would be worth it. Firstly, to have a lambda 2 parameter that varied across track with the carrying noise level variation. Yeah, I think that would be interesting to know, like, firstly, if it's, I guess, of course, that it would be beneficial to adapt it, but of course, I think the computation error would increase. So if it would compensate the improvement we have with the extra computational error, and then with all this gap filling in Nadir using data, I mean, yeah, it's something I have thought about. I know like that some intern students of the team have looked a bit more into it with Emmanuel, and yeah, I think like the Nadir, I didn't consider it at all, but I think it would provide important benefits, although of course it comes with its own noise, so you would have to see how to combine these two noise problems.
But in theory, with your technique, it could be possible to have an extra error term and also an extra measurement point in the center with its own error.
Yeah, maybe also, because here I haven't shown it for simplicity, but there's like a masking term in the equation. So, but yeah, again, it would need to be explored if the complexity added would compensate all the computational.
Yes. Okay. One of the very interesting parts of your variational filtering was the fact that you explored using the 3-order constraint on the different terms of the equation, and then found that it was lambda 2 that had the strongest effect, and so that's a simplified way. Can you explain why physical reasons why that particular term is so efficient? Have you thought about that?
I think it's because more of the also because of the error, like the carrying noise, we can see that the effect of the noise is amplified once we calculate the gradient. So I think that it's like, for me, I see it more like it's that variable that we have to focus in penalizing to recover the the other structures, and that consequently this like noisy gradient then has an effect on the Laplacian. I don't know, yeah, I see it a bit in that way.
Okay, because the amplitudes of those different terms and the amplitudes of the gradients that you're trying to minimize, were they larger for the lambda 2 term?
Yeah, okay, yeah, we could also say that when you calculate the gradient is when you also start to see like the strength of the energy present, no, in our physical signal. So yeah, actually, for example, here in the Mediterranean, our energy levels are lower. For example, if we maybe went back to the California system where there was the study of Gautier et al., maybe there's the signal is stronger even in the gradient. We could see still a bit, maybe have some kind of intuition of some very strong energetically feature. So sorry, I don't know if I'm being clear, but yeah, I think like in the gradient we can see like the high energy levels, and the higher the energy levels, the less we penalize. So at the end, it's like all related, and yeah. Sorry, I'm not being very clear.
No worries. Okay. One of the things that was also striking when you compared our knowledge of those small scales from models is that the three models gave very different results.
Yes.
And you explain that due to the different physics and the different ways the model are representing that balance between the small scales and internal tides, internal gravity waves, etc. But it was also interesting when you used your calibration relationship at the end. You have an estimate, a global estimate now derived from altimetry. How does that match up with your three model results globally?
Sorry, can you repeat? My computer was doing weird stuff.
Yeah, the very last calculation you made was trying to estimate lambda 2 from the altimetric 30-kilometer noise level.
Yes.
Or PSD level. And I just wondered how that global lambda 2 value compared to the three different model estimates of lambda 2 in the regions where you looked at that.
Yeah, well, yeah, like this is like quite a recent results thanks to the data provided by Oscar Vergara, and actually for now I found like there are a bit the lambda 2 values are smaller than maybe what we found, because the PhDs at 30-kilometer wavelengths I have obtained from this collaboration. They're like in the cloud of points, they're like in the higher extreme. So as the higher values, the lambda I need is smaller. But these results are preliminary, and I think I need still to do some checks to see that everything is correct. But it was just to show that from the data we can obtain this real data, and from that tune our parameter.
Yes, because I in the early period of SWOT, it would be useful to use your variational filtering. And I was just wondering how long, how many days you need before you can start to tune your lambda 2 parameter. And if you start from background model data or background NADAR altimetry data, is that a good starting point? And if you have no starting point, how long does it take before lambda 2 becomes stable in your estimates?
Well, I don't.
Sorry, was my question clear?
Well, I don't know. Like lambda 2, like the stability part, I'm not quite sure, because it's like for me like there's this Okay, you say like we have a change in, of course, yeah, our PhD level, of course, it's not stable. You mean it in that sense?
I was just wondering how many repeats of images you're going to need before your technique of estimating the lambda2 parameter is robust or stable.
No, actually, we have like for a certain like time of the year and region, a PhD value of 30 kilometers that is reliable, for example, from Saraltica data. I think that if we have, for example, Saraltica data information one day before, and we manage to retrieve the PhD at 30 kilometers, that can be directly used to know the lambda2 value of the pass afterwards. It can be...
Okay, so you can get it from individual yes. Maps.
I think that as long as we know that spectral value is representative of the specific SWOT data we are measuring, it can be applied. Yeah, I don't think we need several repeats. But then, of course, for example, if we need the, instead of Saraltica, for example, we would want to use the nadir of SWOT, I think further investigation is needed because I don't know how the noise level of the SWOT nadir may compare to that of Saraltica. So depends on that too. But well, at least it's like a possibility that it can be tuned in that way.
In your perspectives, you also mentioned that you could perhaps use the denoising method and then also use other techniques to help refine the small-scale ocean structures, including dynamical interpolation or other techniques. Can you explain a bit more what you had in mind with that?
Like you mean to obtain the 2D gridded maps or further processing of the SWOT?
It was the way of I guess it was in your perspectives of trying to better use the estimate of the larger scale field from other techniques. And so you mentioned using dynamic interpolation, but perhaps other techniques as well.
Well, yeah, for me that is like, if we want to combine the SWOTs now, we need to use of methods like the dynamic interpolation or maybe other methods which are also studied here in the team that, as you said before, like many like studies related on how to combine the SWOT passes are done assuming we already have this noise-free SWOT, and then with our method we give the opportunity to study these methods maybe in a more realistic way, taking into account the a priori errors we have.
Okay. Well, I had a lot of other questions in my report, but I will leave them for the report. And I just want to thank you again for your contribution for SWOT and for the work that you've done, because I think it's a really very good, solid basis for people to carry on then and start looking at the first data using these sorts of techniques. So thank you very much for your presentation and for your responses to the questions.
Thank you very much.
Thank you, Rosemary. So now, Francesco.
So Laura, congratulations once more for your work. I appreciated very much reading your manuscript. I found it very pedagogical, and I think that it was very useful to have a thesis on your subject with the introduction that you wrote, because some of the concepts are new. For instance, you discuss the definition of mesoscale and submesoscale and fine scale, and it's true that these are concepts that are fluctuating a bit in the community in terms of scale definitions in terms of kilometers of dynamics. So it was very good to have a review over this part. And then I found the other chapters also very clear. From my viewpoint, the part that for me was more interesting was especially in terms of the possible implications for in situ experiments. And in that case, the possibility of having a technique to remove some noise and go after the SSH up to vorticity is extremely interesting, and I think it was a thing that has been a bit it has been hidden a bit under the carpet at the very beginning of the SWOT discussions, where most of the focus was on SSH and spectral characteristics of SSH. But it's true that if you have SSH, for many applications, that is not enough. You want to have geostrophic velocities and vorticities, and it was not obvious at all how to overcome the problem of noise. Well, some implications is that from SSH in terms of in situ studies, for instance, in biogeochemical applications, we may be very interested in using the information of the surface to reconstruct the internal dynamics of the ocean. And in that case, the fact of having correctly the gradients of the velocities, so the second order derivatives of SSH is very important. So your method and your exploration for sure will be widely used by the community. In terms of regarding this point, there's something that I did not understand very well. You have a method that penalizes the high derivatives in order to reduce the noise. But at first, when I read this, I did not understand, because I thought if you penalize the derivatives, then you penalize the intensity of the velocity and of the vorticity implicitly. So to me, it was a bit counterintuitive, the fact that it could work even when after you reconstruct the high derivatives to get the signal. So can you clarify on this point, why at the end, even if you penalize the derivative, you are able to reconstruct the derivative with relatively good intensity? And then another thought that I had was that maybe you could penalize the derivatives of higher order than the second one, so that you leave the first and the second derivatives, so velocity and vorticity, relatively untouched, and you still have some parameters to remove noise.
Me actually see, like, when we have the carrying noise, what it does is like increase the values of the gradients. So actually, it's like we have too much gradients, so we need to penalize these gradients which are too much to come back to a more realistic gradient values. So also, as we saw, like, actually just like if we penalize only the Laplacian, it's not enough. We need to maybe penalizing the gradient and the Laplacian is beneficial, but only the Laplacian is not enough. There's like this gradient of the carrying noise that is quite strong, as we can see in, like, for example, in, well, yeah, I don't know what happened, I don't see my screen anymore, which is really high. So may I see this, like, we have like these extra gradients, and our method manages to remove these extra gradients we have due to the presence of the carrying noise. And also like going to further order derivatives penalization, like we saw that when we go to higher order derivatives penalization, the correlation of the method becomes much more complex, and my first guess and intuition would see that if there's some improvement to the method, I don't think it is going to higher order derivatives penalization. It would just like make it more complex and harder to converge, and the effect we would see back in our SSH and the derivatives, I don't think would be very high.
Okay. And do you know whether there is a kind of a wavelet analogous to what you did?
No, not really.
Did you attempt to reconstruct to apply some omega equation or surface quasi-geostrophy starting with your data or?
No, actually it was
yet?
one of the initial, at the beginning of the PhD was something we thought about looking, then the course of the PhD changed a bit, and actually the implementation of the method was more complex than we expected, and we never reached that point.
Yeah, but that would be, but for sure,
Yeah,
someone
but
will
yeah,
do that.
it would be interesting for sure.
Yeah, yeah. We'll see. And then so there is still some of the signal from the derivatives that is lost when you penalize. You smooth a bit anyway the signal. So, do you think that it is something that could be re-amplified after? So first use your method to filter noise, and then you try to put back some of the intensity of the first and
I think
second
that
derivatives.
yeah, I think that especially the vorticity would strongly benefit from studying, also combining this method like with the image like techniques that use the image structure like finite Lyapunov exponents or singularity exponents to make the vorticity structures a bit fine, and also maybe gain back part of the intensity. I think, yeah, that would be a very interesting techniques to combine maybe with the denoise SWOTs.
Not just a factor, that a multiplying factor.
That would be great and much more simpler, but
You're not
no,
optimistic.
I don't know.
Okay. So, well, the next one is more discussion than a question. You know that we are organizing some campaigns during the fast sampling phase. After the experience that you had on the thesis, do you have any recommendation about the type of observations that we could do in situ in order to calibrate and validate not SWOT but your filtering method? So I'm thinking, for instance, the use of surface drifters that could provide some trajectories or even velocities that could be compared with the velocities that you derive from your method. But maybe
Yeah, I
there
think
are some other.
yeah, I think like for looking at I mean, of course, it depends what is the objective of the campaign exactly. For example, if it's more looking at biogeochemistry or more understanding the physical dynamics. But yeah, I think, for example, having information on the surface drifters would be an interesting way to validate the data. Like if we could obtain like trajectories inferred from the denoise SWOT swaths and then compare it with real trajectories from drift, I think that would be some very interesting like fine scale observation data. And then I think, yeah, like any kind of data that can, for example, help also retrieve vorticity, that could also be interesting to compare. And then, yeah, also one of the benefits of this data is again like studying like this, the signal of unbalanced motion. So any kind of data measurement that manages to capture this phenomena. For example, I remember looking in the Mediterranean, it was a bit complicated. I mean, the signal is not very strong, but if there's some kind of internal wave signal, it's a bit difficult to have measurements on that because of the temporal coverage of the measurement, like for example, a lot of glider tracks or stuff like that. So I think, yeah, like.
Well, there will be a campaign around New Caledonia where internal waves are much stronger, so that can be that case a good, especially the comparison between the Mediterranean case and the New Caledonian case could be very nice to see whether your method can reconstruct in both cases, a case dominated by balanced motion and another one where we expect much stronger internal waves.
Yeah, I think that also that could help like better understand the behavior of the SSH spectra at these fine scales. Yeah.
Otherwise, regarding the experiment that is done off California coast, in which the objective there is really to have a precise estimation of the SSH and its spectrum. Do you think that there is some information that you could use to tune your technique or to develop, to improve your technique or to validate your technique?
Yeah, I think like managing to have like data with high enough synopticity that we manage to capture the internal waves would be very interesting. Again, for example, yeah, as I said before, like we were just saying with Rosemary, that at these small scales, the different models we have, for example, they give us different energy levels. So to know, at least in that region, which is the best estimate of the energy level we have. So I guess, like for example, data having like a lot of repeated tracks could help, or even like yeah, the mooring arrays. I think for these fine scale features are very interested, and drifter information. Like it doesn't. I think that not only of drifters, sometimes we have like other drifting information that maybe we can use, like of when the Argo glider are transmitting data. That could be interesting to know if that data can be recycled in some sense and fill some gaps.
And otherwise, in terms of campaigns, is there, if you had to organize a campaign, is there something that you would like to do with your method, or not necessarily related to your method?
I think, yeah, it would be interesting. I mean, we've seen that tuning the parameter with the SSH spectral values at 30 kilometers works, but it would be interesting to know if there's with information on the, for example, having data on the vorticity is more complicated, and seeing if that kind of information can also be useful, I think would be interesting. But well, maybe we see that only with the SSH spectra is enough and it doesn't add anything else. But in case we had like a data gap, that there was no altimeter data, to have a plan B for tuning would be interesting.
Do you have an idea of how to compute vorticity from in situ data? There's an experiment that has been done with 2 ships measuring ADCP
Yeah,
at short
with doing,
distance. Well,
yeah, I mean, then also I guess from those ADCP measurements, I guess it would be important to know down to which scales they manage to derive vorticity. I guess like maybe from drifter information, some kind of information related to vorticity can be obtained too. But yeah, I mean, it's a complex data to
Ananda is
obtain,
not
but
very.
to ask is free, so.
Okay. Then maybe the last thing that I wanted to ask you is what I saw in the last sentence of your thesis says something about preserving and protecting the ocean. So I think that was a motivation for your work. Did you find anything about this with SWOT, or so which part of your work or in general of the experience that you had during your PhD had something about preservation and protection of the ocean?
Well, maybe it's looking too far, but I like to think that if we having this better information to SWOT, will have better information for surface currents that has important implications, like also like for example, managing pollution, or better understanding the impacts of climate change on biogeochemistry. Like, yeah, I think also like I think it's like a small piece, but I think that in some way it helps to contribute to the study of the dynamics of the ocean, that then helps to better understand it and know, for example, where we have to focus our energy.
I think that in terms of pollution, what you did is very, very practical, and it is very easy to implement. So it would be nice to see in the next years whether it will go, if your thesis will go directly into some products that you will see in real time on Copernicus, but that could be. So yeah, I think that that's all from me. Congratulations again. It was very interesting to read and to discuss.
Thank you.
Thank you, Francesco. Well, I assume the three supervisors won't have a lot of questions to ask. So perhaps I may ask my own question now, because it's a little bit, or my own comments. It's a little bit related, quite directly related to some question of Francesco and Rosemary. So first of all, congratulations also. I mean, I really appreciated your presentation. Absolutely not a specialist of image processing and denoising, so I learned quite a lot reading your thesis. And really, it's a thorough and very clean work you did with processing the spectrum. So it's very interesting to me. So I have actually one or two small questions and perhaps a comment. First, a very practical question. When you implemented your either the Laplacian filtering or the variational approach, what did you choose as boundary conditions?
Yeah, there was some. Yeah, of course, it was finite differences. We had to choose some boundary conditions. Yeah, we set some values. They were not periodical. Yeah, there were some values. I don't remember by heart. I have it here.
You used the last value on the boundary of the.
Yeah, like once. Yeah, it was a. I don't remember exactly the calculation, but I used like to find let's say n. I used n-1 to compute the n point. I don't remember exactly what, if it was. What transformation of n-1, but
yeah, which means that the smoothing is not fully done near the boundary.
Yeah, actually for the Laplace, yeah, the borders, the last point I don't take into account is.
Yeah, so my comment here actually, when reading your thesis, is that it's absolutely not a criticism, because you are not a specialist of partial differential equation, I know. But since we are dealing with a diffusion equation for the Laplacian, we can interpret it at a continuous level. I mean, it's a continuous equation.
Yeah.
And actually, it's quite easy to compute the exact analytical solution, at least for assuming an infinite domain or a square or a disk or something like that. And you easily find that the solution actually is the initial condition, your initial solution, multiplied by an exponential proportional to minus t omega squared. Okay. So there's a beautiful, very large table in your thesis with many different values for the number of time step and your parameter lambda or something like that. Okay. And actually, lambda times the number of time step is proportional to the physical time, actually, during which you make this smoothing. And actually, if you look at your table, I did it for three or four figures, and it works perfectly well. I mean, if you divide, for instance, this physical time by a factor of 10, you divide your cutoff lines by a factor of square root of 10. And it's really clear up to the second digit. It works perfectly well, so it's completely consistent with the theory, actually.
Yeah, okay.
And my second remark is about the variational approach. And actually, if you do the same thing, when you compute the gradient and you want the gradient to be 0, you have an iterative process, hk plus 1 equal to hk plus something. You can interpret also this in terms of a continuous partial differential equation, which would be something like dh dt equal to a nudging factor, something multiplied by h ops minus h, plus a b Laplacian, b harmonic, by harmonic. And I suspect, I didn't do it, but I just, actually during your presentation, during the question, I just wrote a few lines. I suspect that if we get a solution in the Fourier space, actually we are looking for the 0 of this gradient, which means that we are looking for the steady state solution of this equation. Okay. And I suspect that an explanation perhaps for the fact that the biharmonic is better than the Laplacian here is simply that in the Fourier space, the slope of the biharmonic operator it's much closer to the slope, the natural slope of the data spectrum in terms of either the spectrum of the data or the spectrum of the noise. I'm not very clear about that. But it's probably much more aligned than the natural slope of the Laplacian. I suspect this is the explanation.
Yeah, actually, like this gave me a flashback of a conversation with a colleague, with Jean-Michel. And that I think that a strong relationship can be found also with the spectral slope. But then, of course, we have the problem that we have like this change of slope that we would have to change. Choose maybe some kind of specify what slope we take into account.
Yeah. But it's related to the cutoff lines actually also. So okay, so just a comment, but I think it could be interesting to try to see a little bit more in depth what is behind this. And so my last question was about also the variational approach. I mean, after the launch of SWOT, perhaps can you expect to get some significant information on the correlation structure of the errors, of the actual errors? And if this is the case, can it be used to improve the method, to improve the denoising method?
If I remember correctly, like I guess, like for example, yeah, like the information, for example, the changing from one SWOT simulator version at the beginning of my work to another, the spectral error models have been adapted as they have more, like, let's say, engineering information of these errors, and the errors I take into account, they're more realistic. Yeah, I mean, I don't really know. I guess like it depends on the engineering, like information we get of the, like, especially instrumental noise. Then of course there's of the geophysical errors, like the C-state bias. I think like the wet troposphere, the correlated errors due to geophysical errors, I think we can have this information. Then of the instrumental errors, I don't know. I can say hopefully yes, but I really don't know.
Okay, thank you. So I assume you've almost finished with the questions. And now perhaps the supervisors, starting with Ananda.
I really appreciated the presentation, and I'm not going to ask questions. I'm just going to make a few comments. So I have really enjoyed these years working with you, and I also would like to particularly thank Emmanuel and Julian for giving me the opportunity of this co-supervision. As you know, well, in the beginning, the first years I have been more involved, and the last year, even if we in contact with the manuscript and also with the last presentation, but it's true that Emmanuel and you have done most of the work during the last years. So I think that it have been very complementary because our background as supervisors is very different, and so I am always learning with them, and so this is very positive, this kind of collaborations among different groups. So I would like also to highlight from Laura that she has always had this curiosity to learn new things. In the conference, when I have spent time with her in the conference, she was always asking questions, going to talk to different speakers, with Brian Arvid, for example, or many others. And also her capacity to overcome difficulties, because it has not been easy always, and but she has been able to continue and to make good progress, and this is the result that we have seen today, and also her publications and etc. And so I know also that she has been successful to get here a postdoc working in Holland with Eric van Seville in the topic of plastics, that I think it's also a good continuation of was also asking before of this thesis also. And also I would like to mention that well, Laura participated with in our experiment that we had a couple of years ago, the pre-SWOT experiment. So that was a first cruise in which we tried to mimic the SWOT sampling, but with in situ data. And so we learned a lot. She was very active during the cruise and very enthusiastic, and we really enjoyed having her on board. And also we learned a lot, and also with the thesis that I think that we can do it better when SWOT will be launched in 2022. So now we are starting preparing the new proposals, and for sure all the material from this PhD and what we have learned will be very useful. And also I would also like to thank all the comments from the rapporteur and from the examinator that are very useful. And in particular with Francesco, we are having also some discussions on the topics of vertical velocities and on the topics of how to better sample the, in the future, and how to compute all these variables like the vertical velocity or vorticity from in situ data, there are also other issues like lacks of synopticity or errors, etc. And also just wanted to end also adding that Laura also has been very interested always in outreach activities. I think you didn't mention, but when Laura was here in Mallorca during certain periods, she spent more than a year here. She was always very happy to participate in all the outreach activities, in the like giving talks to kids or whatever related to. So it has been a real pleasure, and I hope that we will have new opportunities to meet all of us in person. I'm really sorry that I can't make it this time, but hopefully we will get better times soon. And so thank you. Enhorabuena, Laura, una abraçada forta.
Gràcies.
Thank you, Ananda. Julien, you have a mot?
Yes. I'd just like to say a few words, I guess. There's just a bit of an echo. If I don't know if you can lower the volume a bit on your side. Yeah. So first, I'd like to say that I'm actually very happy to even remotely be here. I really enjoy your presentation, Laura, and the way how you managed to improve it every single time we've been rehearsing over the last couple of weeks, and I think it was really a really good presentation, and I congratulate you for this. I wanted to stress that I found that a bit ironic. I mean, the topic you've been focusing on is, as Rosemary mentioned, I believe a very useful sort of work with very clear practical applications. And when I compare this to my PhD work quite some time ago, which was a bit more abstract, I can see that there are different sorts of science, but you can enjoy all of them, so that's good. I'd like to stress that the specific project you've been working on here, I mean, all PhD students should, I mean, they have to deal with lots of information coming from different people with different backgrounds and expertise, but here it was even more complicated because of the very different sorts of cultures and complementary approaches to oceanography between Mallorca, Grenoble, and some applied maths there. I mean, you had to make a synthesis with many sorts of different influences, and you did great in this context. And I'm really happy because this has led to several papers, but also open source code with this denoising code that is now issued with the help of Oceanic and CNES. And as you know how I value the production of source code, I really think it's a great achievement. I'm also, I guess, very happy for you because I know in the beginning of your project you were probably slightly frustrated because there wasn't that much physics in your PhD topic in the beginning, and I know that you were more like driven by the physics, but you actually managed to get over it and embrace really full-heartedly your project in all its dimension and even the methodological aspects, and you really managed to work in such a way that you saw the science behind the methods, and I really I think you enjoyed it, so I'm happy for you. On a more personal side, I'm really happy with this experience because I learned a lot scientifically, but also on the say human relation level through the collaboration with Manu and Ananda. I think it was the first time that we really get to work together, so that's cool. And also because I mean the way how you Laura approach science is not the way how I naturally approach it, and therefore we had lots of occasions to discuss and confront and see things differently, and I really enjoy that. So thanks, Laura, for your energy, your positive attitude, all your efforts, and the quality of the work that came out of it. and thanks for giving me the opportunity to question a bit the way how I interact with students. So that's good. And I also take this opportunity for thanking Ananda and for all our discussions, and Manu for the central role you played in organizing all this project. So thanks. If I may, Brian Arbik sent a question through email, and I think I can maybe pass it on here to Laura. Is that okay?
Yes.
Okay.
Such an honor.
so I'm reading. So Brian was online for the presentation, and he sent this question. So I'm just reading his email here. So the question is, if I had had the chance to ask a question myself, it would be that you might want to mention the importance of studying the solution of the same model run at different resolution. The models all give different results for a variety of reasons, but resolution is surely one of the reasons. To show that systematically, maybe you could, for instance, analyze those two MIT GCM runs, one at 1/24th of a degree, the other at 1/48th of a degree. Is not saying that you should do it yourself, but maybe that could be a nice thing to look at in the future, and he'd be happy to have your perspective on this.
Yes, I believe that, of course, one of the differences between the models would be the resolution, and the way to more consistently look at the effect of this would be to compare two models, like in this case MIT GCM with the same resolution, as well as also with this resolution problem also appears on the SWOT grid we choose. So yeah, I think there's several tests in this case that can be done of the sensitivity that can help us better understand why the differences that I have in my results occur.
Yeah, this is certainly, I think, something that we ought to discuss a bit further, but that's certainly not for today here. So thanks again, and that's all I have to say.
Thank you, Julien. Manu? Merci. Do you mind if I switch back to French? Everybody understands French, I think. Très bien. J'enlève mon masque juste. Je vais commencer par quelques remerciements. Tout d'abord envers le jury, que je remercie chaleureusement pour tout le travail qu'il a réalisé, pour rapporter le manuscrit, pour l'avoir lu, pour se poser des questions, et j'espère que le jury en a tiré profit. Donc encore merci à vous quatre, puisque j'inclus Eric aussi, pour ça. Ensuite, j'aimerais remercier Ananda et Julien aussi, qui ont largement contribué à l'encadrement de ta thèse, Laura. Alors j'ai bien senti que c'était pas toujours. On est trois personnalités, trois façons différentes de travailler. Ça s'est bien senti. Et puis si on compte dedans, c'est 4 personnalités et 4 façons différentes de travailler. Mais en fait, tous les trois, on était quand même toujours d'accord sur l'essentiel. On a trouvé un mode d'interaction qui était peut-être perfectible, mais qui en tout cas était efficace pour l'encadrement de Laura. Alors c'était peut-être pas le mode d'interaction optimal comme on aurait pu le voir ensemble, mais en tout cas je pense que pour Laura on n'était pas loin de quelque chose de bien, et au final j'ai l'impression qu'on a tous, nous les encadrants, extrait quelque chose d'intéressant scientifiquement pour nous. Voilà, donc voilà, tout ça, je vous remercie pour ça, tous les deux. Et puis, je vais, de façon un petit peu formelle aussi, je vais remercier les soutiens financiers. Donc, il y a le CNES aussi, que tu as mentionné, un projet européen. Ce qu'il y a derrière, en fait, sont des collègues de l'équipe MEOM qui ont mis à disposition des moyens financiers pour que la thèse de Laura puisse se tenir dans de bonnes conditions, et qui a dû être un petit peu prolongée, d'abord pour le retard, ensuite à cause du Covid. Et tout ça, ça c'est grâce aux collègues, donc je ne sais pas s'ils nous écoutent, mais en tout cas je les remercie chaleureusement. Ensuite, Laura, pour ce qui te concerne, tu savais que SWOT c'était un sujet sur lequel moi je me suis engagé, enfin je m'engage beaucoup, ça me tient beaucoup à cœur. Donc Tu as peut-être senti, j'avais beaucoup d'attentes sur ce sujet, donc c'est avec beaucoup d'émotion que je t'ai vu aujourd'hui. Je suis très content de te voir finir ton travail en beauté comme ça. J'ai envie de souligner quelques éléments qui m'ont plu dans le travail avec toi. Et le premier, c'est ton enthousiasme et ton optimisme. Tu as toujours le sourire, tu n'es jamais démotivé, ça c'est super. Quelque chose que j'ai vraiment apprécié, des fois même quand c'était dur, bah, tu avais toujours le sourire et tu retournais travailler. Ça c'est vraiment le truc qu'il faut que tu gardes. Et puis un autre truc que je t'encourage à entretenir, c'est ton énergie et ton foisonnement intellectuel. Tu comprends ça? Prolifération intellectuelle. Et idéalement, il faudrait que tu essayes de les coordonner un petit peu.
Oui.
Tu as plein d'autres qualités, je ne vais pas toutes les lister, ça c'est vraiment celles qui m'ont le plus marqué. Alors sinon, pendant ta thèse, ta présentation a bien montré, hein, donc on a beaucoup travaillé avec Julien et Ananda sur ta présentation, mais personnellement, je ne suis pas intervenu dans les derniers ajustements, et vraiment, j'étais enchanté de voir le résultat final par rapport au statut dans lequel je t'avais laissé la semaine dernière. Et là, j'ai eu l'impression vraiment, ça y est, là, tu as fait un pas. Tu as progressé encore, tu as confirmé tous les progrès que tu avais fait. Alors, les progrès, c'est sur les compétences scientifiques, sur les compétences techniques. Tu as développé un outil, tu as publié sur GitHub, enfin, même si techniquement, ce n'est pas toi, ton outil est publié sur GitHub. Tu as exploité ton outil pour des questions scientifiques qui sont vraiment pertinentes et d'actualité. Voilà, tu as acquis tu as considérablement développé des compétences scientifiques, techniques, mais tu ne te rends pas encore compte. Et tu verras dans 6 mois, quand tu seras en postdoc, là tu vas commencer à comprendre, ah mais ouais, là par rapport à avant ma thèse, j'ai vraiment fait un gap. J'ai passé une étape. Donc vraiment, je suis très fier de toi pour ça. Voilà. Et puis, ben voilà, j'ai eu beaucoup de plaisir à travailler avec toi. Des fois, c'était vraiment très challenging de trouver des moyens de te faire passer les messages que je voulais te faire passer, mais on a toujours réussi finalement, et c'était super. Voilà. Donc, je te remercie et puis je t'encourage à continuer. Merci Manu. Bon, écoutez, je crois qu'on va s'arrêter là pour la séance avec le jury. Et puis, donc on va te demander de nous laisser un petit peu, Laura, le temps qu'on délibère.
Ok.